Okay, so as always, please type your name into the chat starting now that the recording has started so that we have a record of everybody's attendance. I hope everybody had a good 2 weeks and a good holiday, and I'm happy to be back with everybody to do a little bit more calculus. Just as a heads up, we have three more classes for this semester. So we have this week, and then we have next week on the 13th, and then we have a week after that on the 20th. And that will be the last class, probably. We're going to be taking a break probably about 1 month. So we're not going to have classes over Christmas and New Year's, and I'm going to be away a little bit at the beginning of January. So after December 20th, we probably resume again in late January sometime. Okay, but we'll get to a good point um, with the three more classes today. Oops. Okay. So I know it's been a long time for a lot of you. So I want to make sure that we go. I don't know. It might be January, probably January 24th, I'm guessing. I'm going to send out a new syllabus for the spring semester. I haven't sent out a syllabus yet. So the syllabus will have the date, but my guess is it's probably January 24th when we resume. That's the next Friday. Although, actually, and I'll talk about this more later on, I think next semester class is not going to be on Fridays because I have to teach at my university um, on Fridays. So I'm going to do a survey about what day might work better for people, but I might want to move it to Thursdays. We'll have to see what works for everybody. In any case, I'll send out messages like this in early January and we'll get a full calendar. I'll get you a full calendar before we start. Um, but yeah, our normal time Fridays at 4 will definitely not work next semester because I'm teaching a class at my university during that time. So I'm going to have to switch the time. Um, Okay. So, but in any case, we'll figure that out. At least for now, through December 20th, we'll be meeting at the regular time. And then definitely we will not meet again until the second half of January. I'll be a little bit more clear when we figured out the specifics. Okay, great. Okay, so let me do a little recall of what we were talking about last time, which was 2 weeks ago. And so people may have forgotten. So the main thing that we talked about last time is that if we were given a function, we defined this other function that was called the derivative of that function. And this derivative encoded two different ideas. One was this tangent problem, where you tried to figure out the slope of the tangent line to a function. And one is the velocity problem, where if a function gives you the position, you have to try to figure out the velocity. And so this was the definition in terms of limits. So if you have a function given by f of x, then the definition of the derivative of f of x, which we usually write f prime of x, was given by this limit. You write f of x plus h minus f of x divided by h, and you take the limit as h goes to 0. This is how we did this. And keep in mind, if you just plug in h equals 0, in the numerator, you get f of x minus f of x. That would just be 0. In the denominator, you also get 0. So you get 0 over 0, which is indeterminate. And that means to evaluate these derivatives, you always need to do something a little bit more creative with the limit rather than just punching in h equals 0. That doesn't work. You have to do something, you have to do an extra step somewhere. And it's also worth mentioning that there's lots and lots of different notations for the derivatives, and I'm going to switch back and forth between using them. All of these notations mean the exact same thing. We just have a lot of different notations because calculus was discovered by different people, and all of the notations survived. So we have f prime of x. That's one way of writing this derivative function. Another way is we have this d dx. This over here is sometimes called the derivative operator. Operator just means something that takes a function and turns it into another function. So if we have f of x, we take d dx of it. That just means we're taking the derivative. Don't worry about what the d and the dx mean. For us, this whole thing is just a symbol. It just means take the derivative. Uh, and then if we're actually talking about it as y equals f of x, then we can also use the notation y prime we see sometimes, or also this notation dy dx. all of these mean the exact same thing. They just mean the derivative function. But it's useful, for instance, in the textbook, if you follow along, you'll see all of these notations, and they're all notations that I'll sometimes use. So it's good to just know them, but there's no extra math here. It's just a bunch of different notations that all mean the exact same thing. Okay, so this is our function. So this is our definition for how to take the derivative of a function. And what we did last time was we came up with some rules for taking derivatives that made it so that we didn't have to actually evaluate this limit every single time we want a derivative, right? So the rules we had last time, we had three major rules. Okay, the first rule is the most useful rule. This is called the power rule. And this said that if f of x was x to the n, if you have a function that's just x raised to some power, then the derivative is always n times x to the n minus 1. So if f of x equals x cubed, then the derivative is 3 times x squared. And we actually prove this whenever n is a natural number, but it's in fact true for any real number n at all. We did not prove that, but we'll use it for now. So no matter what you have, x to the 1/2, x to the -5, x to any number at all, when you take the derivative, it's always going to be n times x to the n minus 1. Okay. So this is the power rule. We'll go over the homework after this. I just want to recall these rules before we go over the homework. So the other two rules we did were the constant multiplication rule. So if I have a function and I multiply it by some constant, c over here, then, so my new function g is c times f, then the derivative of that function is just the derivative of f times the same function c. So if the derivative of x cubed is 3x squared, then the derivative of 2x cubed is 2 times 3x squared. A constant can just come along for the ride. Okay, if you multiply the function by a constant, the derivative is multiplied by the same constant. Okay, so multiplying function by a constant multiplies the derivative by the same constant. So this was called the constant multiplication rule. We'll see this applied in the homework. And then the last rule we had was called the addition and subtraction rule, which tells us that if we have a function that's a sum of two other functions, or that's a difference of two other functions, right? That's what this plus minus means. It means it could either be a plus or a minus. If you have a sum or a difference of two functions, then the way you take the derivative is to take the derivative of each of the two functions and then add them if it's a sum or subtract them if it's a difference. Okay, so if I have something plus something else and I want to take the derivative, I just take the derivative of each part and I add them. If I have something minus something else and I want to take the derivative, I just take the derivative of each part and I subtract them. Okay, and in the homework, we'll see an example where we get practice with this. Okay, so these are the three basic rules that we had for computing derivatives. There are going to be more that we're going to talk about, not really today, but next time. But for now, we have these three basic rules for doing derivatives. Okay? And all of these mean that when you want to take a derivative of a function that you can build out of this, like a polynomial, that you don't need to do this limit. You don't need to do this x plus h, x, whatever. If this limit is hard, you can just do the power rule, which is much faster. Okay. Okay, so now we came back for these homework exercises. So this was the first homework exercise, which is just an exercise in applying all of these rules. So we want to calculate the derivative of this f of x, which is this polynomial given by 3 times x to the fourth minus 5 times x squared plus 7 times x minus 4. So does somebody want to do this one through? So remember, we have these rules, right? And so in particular, we have the addition and subtraction rule, which means that we can just do each of these pieces individually and add and subtract the answers, right? So let's say we want to do the first one. We want to do the derivative of 3x to the fourth. right? So if we have the derivative of 3 times x to the fourth, well, using the power rule, what would the derivative of x to the fourth be? This is the power rule. F of x is x to the fourth. So what do we get if we take the derivative of x to the fourth? Okay. Okay, so I mean, I'll just do it, right? So the point is, what is this with 3x to the fourth? We get 3 times the derivative of x to the fourth, which by the power rule is 4x cubed, right? So the x to the fourth becomes 4x cubed. And by the constant multiple rule, right, what we really can do is we can just move the 3 out of here. So the 3 just stays along for the ride. And this becomes equal to 12x cubed, right? So I'll do this with all of the other terms also. So d dx of 5x squared, that's just going to be 5 times the derivative of x squared, which is 2x to the first, right? We bring the 2 down and it decreases by 1, becomes a 1. And so this is otherwise known as 10x. Then we can take the derivative of 7x, which is 7 times the derivative of x, which is 1x to the 0. But 1x to the 0 is just 1, right? So this is just 7. And then if we take the derivative of the last term of 4, well, 4 is what 4 really is that's 4x to the 0th. And that's going to give you 4 times 0x to the minus 1, right? This is what happens if you pull down the 0. But 0x to the minus 1 is just 0. So this whole thing is just 0. So the final answer is that f prime of x, we've done each of these individual terms, and now we have to subtract, then add, then subtract. So what we get here is 12x cubed minus 10x plus 7. And then if I want to write minus 0, I can. You don't have to write minus 0 because it doesn't do anything. But this is the derivative. So I'll put here minus plus minus. Okay, so this is an application of all of the rules, right? We've done an application of the sum and difference rules. That's how we did each of these by itself. The constant multiple rules, that's how we dealt with all these constant multiples. And then the power rule, which is how we actually differentiated. Remember, differentiate is the verb for take a derivative. It's called differentiating, is how we differentiated these individual terms with the x to the fourth, the x squared, and the x. And by the way, I'm writing these down to be very kind of pedantic, but it's probably worth it to just remember that the derivative of x is 1 and the derivative of any constant is 0. Right? Because remember, derivative represents a slope. So x has slope 1, a constant has slope 0. So the derivative of x is going to be 1, the derivative of a constant is going to be 0. All right, any questions on this example?
Hello, Russ.
Okay, all good? Yep, James?
Yeah. If you find a derivative of a number, like example, you have a derivative, or if you find a derivative and you have a lectern, can you add them?
If you have a what term?
Yeah, if you find a derivative of two different terms within in a function and they are lectern, like maybe you have a derivative of 2x squared minus 4x squared. If you
Oh,
find a
like
derivative
terms,
of
yes.
oh, okay.
Yeah, so you can
Hello?
either do, right, so you can either take the derivative separately and add them, or you can add them before you take the derivative. Either way will work. You'll get the correct answer both ways.
Oh,
So
okay.
usually it's
Okay.
nice, it's better to just simplify them before you take the derivative, but you don't have to. You can do the like terms separately and add them afterward. That's fine too. Yeah, they all work. Okay. Princeton, yep.
Yeah, hello.
Yes, Princeton. Yes, yes, I'm getting you.
What if what plan has a special time?
Sorry, actually, I'm not getting you, so you're not coming in so clear. Prince,
Hello.
hello, yes.
Yeah, I'm saying, what if one part of the team has a fractional pack? The example, we get 3 raised to the 4 power or what 2.
That's fine because a fractional part is still the same thing as a constant, right? Because if you have, if I'm taking the derivative, let me just put it over here. If I'm trying to take the derivative of, 4x to the fifth over 3, something like that. Sorry, ddx of
Okay.
4x to the fifth over 3. This is the same thing as it's still a constant. It's 4/3 times x to the fifth. And so by the constant rule, that's the same thing as 4/3 times the derivative of x to the fifth, right? So we can pull out the numerator and the denominator because it's all just a constant. In this case, the constant is 4/3. So we can pull that out. And so this becomes 4/3 times 5x to the fourth, or 20/3 times x to the fourth. Okay, yeah. So as long as it's constants, then numerator, denominator doesn't matter. You can always pull it out.
Okay, so that means can the power also take on a negative root? Negative
Yeah, as
power?
a negative power is fine,
Yeah.
right? Remember,
Yeah.
so the power rule, what we said here is if f of x is x to the n for any real number n, it works. So it's okay if n is negative, fractional, irrational, anything. Any power is fine. So this
Okay.
works for any real number n.
So does a derivative power also have a fractional part?
Yeah, that's fine. Fractional parts are all fine. Everything's okay. You just always bring it down and then subtract 1 from the exponent.
Okay.
Okay.
Thank you.
You're welcome. Other questions? Okay, let's move on to the next problem. Okay, so the next problem says calculate the derivative of f of x equals square root of x minus cube root of x. And the hint, this is good. So actually, Princeton, this question is good because it'll be relevant for this problem. So can we write this in a form where we can use the power rule? Right, so I wrote it as square root of x minus cube root of x, but what's another way that we can write this so that we can use the power rule? Yeah.
Yes.
Yep.
Yes.
Yep. Oh, Princeton,
Princeton.
sorry. Yeah, Princeton.
Yeah, I think to use the first one will be the s raised to half
Mm-hmm.
minus s raised to 1/3.
Great. Perfect. Right. So if we do this, then we can use the power rule and the subtraction rule, right? And so what happens now when we take the derivative?
Hello?
Yeah.
Hello?
Hello, yes.
Hello?
Hello, yeah, Enoch?
Yeah, I think my network giving hard time. So like
Oh, sorry.
the comment was saying, yeah, so like he was saying he's quite correct. You can reread the square root of x as x raised to the power 1/2, and you can rewrite the cube root of x as x raised to the power 1/3.
Mm-hmm.
So yeah, in now the power rule now you are taking the power of x to be 1/2 and you break it down or to be the coefficient for x.
Mm-hmm.
Then they seeing 1/2, you subtract 1 from there,
Mm-hmm.
which you are going to have negative 1/2.
Great.
Then the 1/3, you bring out the coefficient for the x, which will be 1/3x. Then the same 1 over 3 minus 1 from there, which you have negative 2 over 3. So
Perfect.
you have x to the power negative 2 over 3.
Great.
Now we know that, yeah,
I mean,
we
we can
know
leave it here, or
infraction.
we can simplify if you want. Yeah. So keep going.
Okay, yeah, so infraction, whenever we have a raised to the power negative 1, it means 1 all divided by a. So which means, yeah, now we have s raised to the power negative 1 over 2, which will be 1 over 2 times s, or 1 all divided by s to the power 1 over 2. Okay, so, and we know that s to the power 1 over 2 is same as square root x. And also read the 1 over 3, the s to the power negative 2 over 3 as the cube root of s squared. So
Right. So I'll just do
yeah, so it's
the
1
one
over 3.
step here
Yeah, so
and then right. Yeah.
yeah, so if you like, you stop there, but if you like, you can still simplify further to read it in square root form. Okay. So now from there, if you stop at any of the 3 levels, you will still be correct.
Right. Exactly. So all of these are also correct. It's just a question of how much you want to simplify. Okay, so we can leave it with negative fractional exponents, but a lot of people don't like negative fractional exponents. They're a little harder to understand. So if you can rewrite it in this form, this is maybe, it's a little bit easier to understand. 1 divided by 2 square root of x minus 1 divided by 3 cube root of x squared. Okay, so either of these forms is fine, but also the original form is fine. Okay, any questions on this problem? Okay, good. All right, we're fine. Okay, so let's move on to exercise 3, which is a little more conceptual. So remember, we had an addition rule and a subtraction rule. Now let's say we have multiplication. So suppose h of x is f of x times g of x. So the question is, do we have a similar rule for the derivative of a product? So do we think that h prime of x is equal to f prime of x times g prime of x? Can we do the product of each one and then just multiply them together? This is what I say here. Is the
Yeah,
derivative of the product
yeah,
of the derivatives? And if you think this is not true, I mean, maybe you know a rule for how to actually do this, which we'll talk about next time. But the real question is, if this is not true, why can it not be true? What's an example that shows that this is not true? Yeah. Okay,
yeah,
yeah,
hello?
enough. Yeah,
Yeah, yeah, it's Enoch.
yeah.
Yeah, we know at first for this, it will not be true because, uh, note, anytime you have the derivative of a function, is always the slope of that, of the tangent line of that function. So now, if you have f of x multiplied by g of x to be the function, if you are taking the derivative, if you take, if you separately take the derivative of f of x and separately take the derivative of g of x and multiply them together, then which means you will be wrong.
Right. So let's
So
let's
they
yeah. Keep
Yeah,
going.
so the idea behind the function that, because it is always proving that anytime you get the derivative of a function, it should be the slope. So now, if you do this to be proving the slope, it will be wrong. So in this method, you have to take the two of them in respect to the respective derivative. For example, you will first take the derivative of f of x and multiply by the pure, or the neutral g of x. Then you do the subtraction rules, which is you do the addition rather, which you do plus the derivative of f or g of x times the pure f of x.
Yeah.
So now, if you prove this, you are going to get the slope of a tangent line.
Right. So in fact, so this is true. So in fact, there's a rule called the product rule, which we'll talk a little bit about more next time. So the actual rule is a little more complicated than this. It's that h prime of x is f prime of x times g of x plus f of x times g prime of x. But even if you didn't know this rule, what's a way that you can do? You can just check, right? So you can just check an example, right? Even if we don't know the right rule, we definitely know that this rule is wrong. So for instance, let's say that I have f of x is equal to x and g of x is equal to x, right? This is just an example. That means that h of x would be f of x times g of x, which would be x squared, right? So now let's evaluate both sides. So what happens if we evaluate both sides? Well, h prime of x, that's the derivative of x squared. We already know what that is. That's 2 times x, or 2 times x to the first, which is 2x. But if I do f prime of x times g prime of x, well, f of x is x, g of x is x. So the derivative of x we know is 1, and the derivative of x is 1. So multiplying those derivatives, we get 1 times 1, which is 1. And 2x and 1 are certainly not the same function, right? So even if we don't know, so what Enoch said is the correct rule for the product, but this is probably not clear why it works to everybody. I mean, we'll explain it next time why it works. But for now, even if it's not really reasonable to come up with this on your own without having seen it. But what is reasonable is to know that this rule can't be right, because you can just check an example and see that this rule gives you something completely wrong, right? H prime of x is just not f prime of x times g prime of x, because you can just try a simple example and see that it doesn't work. Right? And there's lots of other examples that you can try also, and show that none of these examples work. Okay? So whatever the rule is, it's definitely not this. Okay, so it's not going to be as simple as the addition rule or the subtraction rule. It turns out it's this somewhat more complicated rule, and there's also a division rule called the quotient rule, which we'll also see next time. But at the very least, already, without knowing anything more, we can already tell that the rule's got to be more complicated than just the product of the derivatives, because product of the derivatives gives you a wrong answer here. Okay. Comments or questions? Okay. So, okay, there's no comments or questions. Hopefully this refreshed your memories if it's been a while and you don't remember how this worked. Basically, we had methods for taking the derivatives that apply to polynomials and maybe some functions that are a little bit more general than polynomials, where you have fractional or negative exponents. Okay, so let's start the new material today. By the way, I should say new material, if you're following along in the textbook, the new material is from sections 2.2 and 2.3 in the textbook. Okay, next time we're going to do 2.4. Okay.
Yeah, man.
Yes, question? No? Okay. So I want to talk a little bit. There's a couple of theoretical things we have to do before we talk about examples. We'll do some physics applications today. So first of all, let's say that we have a function. We're talking about this derivative like you can always do it. But the fact is, for some functions, you can't take the derivative. Okay, there are some functions where the limit that defines the derivative is not going to exist. Okay, and if you have a function like that, you just can't take the derivative. Remember, the derivative is defined by a limit. If that limit doesn't exist, then there's no derivative. For polynomials, this is not a problem because we know how to do it. So the definition that we make is that if we have a real number a and the limit defining f prime of a exists, we can take the derivative at a, then we say that f is differentiable at x equals a. Okay, it means we can take the derivative at x equals a. Remember that we have two things. Remember that f prime of a, you can write it in two ways. You can say it's the limit as x goes to a of f of x minus f of a over x minus a, or f prime of a is the limit, it's just the general derivative formula with an a instead of an h. So the limit as h goes to 0 of f of a plus h minus f of a over h, right? Both of these are correct. Okay, so if we can evaluate these limits, if the limit exists, then we say that f is differentiable at x equals a. And so it turns out that if a function is differentiable, then the function is automatically continuous. Okay, so this is a fact. You can read the proof in the book. I'm not going to do it, but you can read the proof in section 2.2 if you want. The converse of this is not true. So if you have a continuous function, that doesn't necessarily mean it's differentiable. So I want to give a graphical approach to start. We'll do an algebraic approach and a graphical approach to see what types of functions can you not take derivatives of. Okay, because it's important in any application that you want to do a derivative, and we'll talk about applications over the next couple weeks, that you need to know that taking the derivative is valid in the first place. Otherwise, you can't do these applications taking derivatives. Okay, so let's do an example of a non-differentiable function. Let's consider the function f of x equals the absolute value of x. Okay, so I'm going to draw the graph of f of x equals the absolute value of x. I'm going to draw it in red. So y equals, sorry. Okay, so I want to draw, this is y equals absolute value of x. So what does it look like? Well, remember, when x is positive, the absolute value of x is just x. So this looks like y equals x. But when x is negative, the absolute value of x is still positive, right? So it looks like negative x when x is negative. So the graph of y equals absolute value of x looks like this. Okay, right? It increases, right? You know, if this is 1 over here, this is 1, but at x equals -1, you also get the point 1 here on the graph. So the graph of the absolute value function looks like a V with the two sides are reflections of each other. Okay, so this is the graph of y equals x. And we want to check whether or not it's differentiable at x equals 0. Okay, and I mean, spoiler alert, it's not. And the reason it's not, what we're going to see graphically, is that functions that have corners like this are not going to be differentiable. Okay, a function with a corner is not going to be differentiable because there's not going to be one well-defined slope of a tangent line. But let's try this. Let's actually just evaluate this. So kind of graphically, we can say it's not going to be differentiable because there is a corner. Okay, we'll see why this means that it's not differentiable. I mean, I didn't tell you, I only gave you an algebraic definition for differentiability, but I'm going to tell you that the visual interpretation of that is that things that have corners are not differentiable. Things that are smooth are differentiable. But let's actually just do this algebraically, right? So if we want to know whether it's differentiable at x equals 0, well, this is the absolute value. This is not a function that we have a formula for. We can't use the power rule here. It's not a polynomial. So what we have to do is actually just go back to the limit. We have to see, okay, so f prime of 0, we have to go back to our formula over here for the limit as x approaches 0 of this quotient. So maybe I'm going to use this first definition. Okay. So f prime of 0 by definition should be the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Well, this is the same thing as the limit as x approaches 0. F of x is the absolute value of x. So this is absolute value of x minus absolute value of 0 over x minus 0. But this is just 0 and this is just 0. So this is just the limit as x approaches 0 of the absolute value of x divided by x. Okay, this is what it simplifies to. So now we have to evaluate this limit. Well, because this function looks like it's doing two things depending on whether you're positive or whether x is negative, we should probably evaluate this limit from two sides. So now, if I take the limit as x approaches 0 from the positive side of absolute value of x over x, well, if x is approaching 0 from the positive side over here, the absolute value of x all of these x's are positive, which means the absolute value of x is just x, right? So this is the same thing as the limit as x approaches 0 plus of just x over x, right? We're positive. Absolute value of x is just x. And well, this simplifies to 1, right? To the constant 1. And so this is just 1. But on the other hand, if we take the limit as x goes to 0 from the negative side of absolute value of x over x, well, this is the limit as x approaches 0, from the negative side. Well, these are all negative numbers. For a negative number, the absolute value of x is minus x, right? The absolute value of minus 2 is 2, which is minus 2, right? To get the absolute value, you have to negate the number. So this is the limit as x goes to 0 minus of negative x over x. And this simplifies to minus 1 everywhere, right? And so the one-sided limits are not equal. One-sided limits don't agree. So the limit does not exist. Okay, does not exist, DNE. Okay, because the one-sided limits don't agree, right? It's different depending on whether you come from the left or whether you come from the right. So the limit over here doesn't exist, and that means that the function is not differentiable, right? So f not differentiable, I'll just write diff period at x equals 0. Okay, because we try to take this limit that gives us the derivative, and we see from one side you get 1, from the other side you get minus 1. Doesn't exist. And graphically, what's also going on here, the idea is when you're to the right of 0, the slope of the tangent line is always 1 because the tangent line is just the line. So it's a straight line. The tangent line is just the same line. Here you always have a slope of 1. Here you always have a slope of minus 1. And at 0, it's impossible to define the slope because you don't know whether you should use the minus 1 or whether you should use the 1. Okay? So these limits don't agree, and that means the overall limit doesn't exist, and that means that the function is not differentiable. Okay, and what we see here is that, right? Why does the corner matter? The corner matters because the slope kind of suddenly goes from 1 to minus 1. It doesn't gradually change. It instantly changes from 1 to minus 1. That slope instantly changing is exactly what a corner is, right? It's the slope changing immediately. Okay, so because it makes this abrupt change, there's a corner which is going to indicate it's not differentiable, and algebraically, the way we see it is that the limits from the two sides are different. Okay? All right. Okay, so any questions? Any questions there? Okay. Okay. All right. So let's move on. Okay, so this is not differentiable, and we can see it like that. So there's another example of something that's not differentiable. Let's consider the function f of x equals cube root of x. So this is continuous at all the real numbers, and we're going to check whether or not it's differentiable at x equals 0. So again, I'm going to draw the graph. This you may have to do on a calculator, if graphing calculator. But what the graph of x cubed, of cube root of x looks kind of like this. Let me actually draw that a little better. Okay. This is what the graph of y equals cube root of x looks like. Kind of makes sense, right? Positive numbers have positive cube roots. Negative numbers have negative cube roots. the cube root starts off increasing really quickly, but as x gets bigger, the cube root doesn't increase so fast, right? The cube root of 1,000 is 10, and the cube root of 1,000,000 is 100. So you have to go from 1,000 all the way to 1,000,000 just to get the cube root to increase from 10 to 100. So this flattens out a little bit in both places. So this is what the graph looks like. And if you try to draw the tangent line here, what happens? The tangent line here is vertical. So it turns out the tangent line here is actually this vertical line if you draw the tangent line at x equals 0. So this has a vertical tangent line. And a vertical tangent line doesn't really have a well-defined slope. You should think of the slope of a vertical line as being infinity or as being undefined. Okay? Slope equals infinity, and so what that means is that we're not really going to be able to have a derivative. Right? Vertical tangent line, I'll say at x equals 0. Right? So what about x equals, well, negative x to the 1/3 shouldn't be any different, right? I mean, it's just going to be the same thing reflected over the x-axis. So that'll have the same situation. We'll also have this vertical tangent line. So let's see what happens if we do this algebraically. All right, so this time we're going to use the power rule. So f of x is cube root of x, and we've already seen in the homework this is the same thing as x to the 1/3. So f prime of x is going to be, we already did this, it's 1/3 times x to the negative 2/3, which is the same thing as 1 divided by 3x to the 2/3. And if we want to simplify it even further, that's 1 divided by 3 times the cube root of x squared. Okay. So now what is f prime of 0? Well, f prime of 0 would be 1 over 3 times 0 squared. And this is undefined. You can't have a 0 in the denominator. Okay? And so what this is going to mean is that so f is not differentiable at x equals 0. Okay? So this is another way that a function can be not differentiable. What happens is you try to evaluate the derivative and you get something undefined. It doesn't work, right? Even though the formula makes sense, and this is fine as long as you plug in any value of x other than 0. But if you plug in x equals 0, then you've got a 0 in the denominator. This becomes undefined. It doesn't work. Okay? So this is a vertical tangent line. This is also another example of a function that does not have a derivative, at least at one point. So we see kind of two different ways that a continuous function can be not differentiable, right? We could have a vertical tangent line or it can have a corner. And basically that's it. Everything else, as long as there's no corner and there's no vertical tangent line and the function is continuous, then you can always draw a tangent line, which will always mean that the function is differentiable. So this is not something we have to spend too much time thinking about, but it's just a caution that sometimes you don't have a derivative, and it's generally for one of these two reasons, either because the tangent line is vertical or because, like the absolute value function, we have a corner, something like this. Okay. Any questions here?
Mhm.
Yes, Princeton?
You the answer question, brother.
Sorry, not coming through clear.
Hello.
Hello, yeah, I can hear that you're talking,
Hello?
but yeah, better.
Hello?
Yes, much better.
Yeah, I want to ask a question.
Hmm.
If is it constant that if s approaches 0 is not differentiable? Is that a constant rule?
You wouldn't say that it's as x approaches 0, it's not differentiable. We'd say that it's not differentiable at x equals 0. It is
As-
differentiable everywhere else. I mean, we could do
Okay.
this. We could do this with a limit also. Maybe this will make sense. Let's do it with a limit because that's how you have x approaches 0. Let me add another method. So with what did I just do here? So with limits, right, f prime of 0 would be the limit. We can do it the same way we did before, as x approaches 0 of f of x minus f of 0 over x minus 0. That's equal to the limit as x approaches 0 of cube root of x minus cube root of 0 divided by x minus 0, which is the limit as x approaches 0 of cube root of x divided by x, because everything else is 0, which is the limit as x approaches 0, right? What is cube root of x over x? That's x to the 1/3 divided by x to the 1. When you take the quotient, it's x to the negative 2/3, which is the limit as x approaches 0 of 1 over x to the 2/3. And this again is, is either infinity or undefined, equals infinity, or, does technically, when a limit's infinity, that means it doesn't exist. Okay? Because again, you have a denominator going to 0 and you've got a 1 in the numerator. So we can also do this with limits and show that the limit that we want does not exist.
Hello.
Hello, yeah, Enoch?
Yeah. Did you say if the limit is infinity, it means it does not exist?
Yeah, I mean, it's a matter, sorry, it's a matter of custom notation. So technically, we say that a limit only exists if it's finite.
Oh,
Okay?
okay.
Now, of limits that don't exist, it can be useful to label some of them as being infinity or being minus infinity. There are other
Oh,
limits
yep,
that
yep,
truly don't exist. They're not even infinity
yep.
or negative infinity. But usually, but technically, for the purposes of saying whether something is differentiable, it's differentiable when the limit exists. Infinity counts as not existing in that
Yeah,
context.
because even for this function where s or f of x is equal to the cube root of x, it
Mhm.
is only they are only at, it might be probably at three different values that you will get the limit or get different value. One
Mhm.
is if you have f prime or 0, you have a limit does not exist. If you have f prime or negative infinity, you have negative infinity. If you have or f prime or positive infinity, it will be positive infinity. But any other value, this limit gonna exist. For example, f prime of 1, f prime of 0.01, f prime of 3, f prime of 5, it will still exist.
Yeah.
Besides,
Mhm. Yeah, those are all fine. And then the question, of course, is f prime of infinity, what does that mean? Really? Right? You have to think a little bit about what f prime of infinity or f prime of minus infinity mean, right? We haven't really defined those either. So of the things that we've defined, it's f prime of 0, which we know what it means. And when we try to figure out what it actually is, it just doesn't exist. Okay, it's not a number.
yeah, sure.
Good. Okay, other questions? Okay, so let's move on. So should mention there's something called higher derivatives. So when we take the process of taking the derivative can be repeated. So we can take a derivative and take a derivative again and take a derivative again and so on. And so this is called taking the second derivative or taking the third derivative and so on. And so the notation is we already know the derivative of f of x is f prime of x. If we take two derivatives, the second derivative is called f double prime of x. The third derivative is f triple prime of x, the fourth derivative f quadruple prime, and so on. And there's an alternative notation, which is that the nth derivative is sometimes written f to the n of x, but that n is always in parentheses. So instead of saying f double prime of x, we could also say f second derivative of x. We put the 2 in little parentheses up here. So for instance, we can calculate the first, second, and third derivatives. This is the same function that was in the homework. So we already have that f prime of x from the homework. We saw this was equal to 12x cubed minus 10x plus 7. So to take a second derivative, we just do the same thing again, right? We do f double prime of x, just means take the derivative again of this. So we can use our product rule and we can use the product rule and the quotient rule. Sorry, not the quotient. Sorry, we can use the constant multiple rule and the addition and the subtraction rule and the power rule in the same way. So now we're just taking the derivative of 12x cubed, so that's 12 times 3x squared, minus 10 times the derivative of x, which is 1, and then plus the derivative of 7. 7 is a constant, so its derivative is always 0. And this comes out to be 36x squared minus 10, right? That's the second derivative. It just means take the derivative and take the derivative again. And now to do the third derivative, we just do the same thing. We're now taking the derivative of what we got when we did the second derivative. We just do it again. So the 36x squared, this becomes 36 times 2x to the first. And then the minus 10 is again a constant, so that just becomes 0. And simplifying this, this becomes 72 times x. Okay. So this is our first derivative. This is the second derivative. And this is the third derivative. Okay. So higher derivatives are not that complicated. It just means take the derivative and take the derivative again. And if you mean a third derivative, it just means do the derivative 3 times. If you say a fifth derivative, it just means do the derivative 5 times. Okay? Now we're going to see later today what these things mean. We already know what a first derivative means, right? A first derivative, it can represent velocity or it can represent the slope of a tangent line. Right? It's maybe not clear yet what a second derivative means or what a third derivative means. So we'll see one interpretation of that today, what they mean. We'll see some other ones later on. Okay? But in terms of as a computation, it just means do the derivative and do the derivative again. So to do 3 derivatives would give you 72x. We can keep going even if we want. If we wanted to do a fourth derivative of x, that would just be taking the derivative of 72x, which is just 72.
Yeah. Yes. So which means this function now, this 3s to the fourth, it only stops at 4 derivative. From fifth up now, it will be 0. It stops at fifth.
Exactly, right? We see the 72x becomes 72 when we take a fourth derivative. And then when we take the fifth derivative, the constant just becomes 0. And once it's 0, any further derivatives will all also be 0, right? We
Yeah.
0, 0, 0,
hello.
0. Yes.
Hello.
Yep.
That was.
Yep.
Yeah, it's something I can always be thinking. Giving the function, for example, getting s squared, or let's just say s cubed.
Mm-hmm.
Now, yeah, it has been shown that if you take the first derivative, which would be like 3s squared, it will be the slope of the tangent line.
Mm-hmm.
And what in physics they also refer to it as, because for example, if you are giving a function a certain value, for example, the car accelerates, or for example, they give you the function of the car to be s of t, which means the function s at the function of t is equal to t squared minus 2t plus 4, just like that. So if they give you the function now, you differentiate for the first time and put in a value, just a single derivative of that function. You put in a value, it will stand to be the velocity of the car, right?
Mm-hmm. Yep, exactly right.
Yeah. So now if you're going for the acceleration, you will have to differentiate 2 different times to then you put in a same value they gave you to get it a meter per second square to get the acceleration, right?
Yeah. So yeah, we're going to see some examples of this.
Yes. Yeah. So now what I'm thinking is that what if you are going for like you are differentiating more than 2-3 times. For example, you are differentiating 3 times. What other method is that?
What does that correspond to? Yes.
Acceleration?
So yeah, it doesn't have as intuitive a meaning as 2 derivatives. So the rate of change of acceleration, sometimes it's called jerk, but it's not really clear what jerk means. It's hard to say what it means beyond just it's about how fast your acceleration is changing. And then 4 derivatives, sometimes called kurtosis. There's all sorts of weird words that people use for this. But the fact is, beyond 2 derivatives, it's harder to intuitively understand what's going on.
Yeah, because in mathematics, some things that I always go through by myself. It was just some part of 2 months ago that I saw something like the volume, the volume and that perimeter of a cube.
Mhm.
The volume and area of a cube. So which means if you integrate the function now, you get a volume and that if you differentiate then you get the area. So these are something I was just thinking last night. It was looking so funny to me.
Okay, yeah, yeah. So we're getting a little off track with that, but I think the idea is there's going to be sometimes you might want to. I mean, we'll see this more later on. I don't want to dwell on it too long, but you can imagine that you want to find you have motion of a particle and you want to know when the acceleration is the fastest. Maybe it's like a rocket ship, and you want to know when the acceleration is the fastest because the acceleration is what the astronauts are going to feel when they're in there. And in order to figure out when the acceleration is the fastest, you actually need to take the derivative of the acceleration and set that to zero. That's kind of a maximum acceleration. So that would be a potential application of a third derivative. But it's not as clear what it means. So for everybody else who maybe doesn't know this, we're going to talk about this, second derivative today, what it means. But for now, we just have a mathematical process, which is we can take as many derivatives as we want, although with this function, eventually things turn out to be zero. Okay, let's move on a little bit from here. So this is kind of what Enoch is talking about. So interpretation of higher derivatives, what do they mean? So suppose that we have that f of t represents the position of an object at time t. And we're always, for single variable calculus, we're always assuming the object is moving in a line. So we've already seen that f prime of t represents the object's velocity at time t. And however your t-axis is oriented, positive velocity represents forward motion and negative velocity represents backward motion. And we also know that in complete generality, the derivative of a function represents the rate of change of that function, right? Or the instantaneous rate of change of that function. That's what the derivative means. So what should f double prime of t represent? Well, f double prime of t is equal to f prime of t prime, right? It's the derivative of f prime. So it's the derivative of the velocity function. Or in other words, it's the rate of change of the velocity function. It's the rate of change of the velocity function. And what is the rate of change of velocity in physics? Well, we have a word for that. What changes our speed or changes our direction? That word is called acceleration, right? So this is the acceleration function. Okay, so if we have f of t representing position at time t, then f double prime of t, two derivatives, represents the acceleration of f at time t. Okay? And a lot of times we know acceleration is important because from Newton's law, right, force equals mass times acceleration. If you know the forces in a physics problem, what that's usually telling you is the accelerations. Okay, and you want to figure out the rest of the motion from that, right? But usually the way forces interact with motion is through acceleration. Okay, so this f double prime, shows up, second derivative shows up a lot in physics. Okay, so any questions just about the concept here? That f prime is the velocity, that's the rate of change of position, and f double prime is the acceleration because that's the rate of change of velocity, right? It's telling you how fast your velocity is changing. That's the acceleration. Okay. So let's talk about this with a problem. Okay, so as we said here, f double prime of t represents the acceleration of the object at time t. This is the rate of change of velocity. So example, if we have a ball dropped from the top of a building, this is kind of similar example to what we had before. So here you are, you're standing on the top of a building, and you've got a large hand, and you're holding a ball. I can't draw very well, so here we are. We've got a ball. Okay. And then we have the building has position 4.9 times t squared, where f of t is measured in meters below the top of the building and t is measured in seconds. So we kind of have like a downward pointing t-axis. So we want to know, what is the acceleration of the ball? So this is relatively simple. So f of t here is 4.9 t squared. This is the position function after t seconds. F prime of t is the derivative, so that's going to be 2 times 4.9 of t, right? Because we bring the 2 down and this becomes a 1. Or in other words, this is equal to 9.8 times t. That's the velocity. And then f double prime of t is the derivative. You have 9.8t. This is t, the derivative of t is just 1, and the constant stays along for the ride. This is constant multiple rule. We get 9.8. This is the acceleration. Okay, and in terms of units, the position is measured in meters, the velocity is measured in meters per second, and the acceleration is actually measured in, you should think of it, it's a rate of change of velocity. So it's your velocity per amount of time. So it's like meters per second, or how it's usually written is meters per second squared. Okay, this is the units that acceleration is measured in. And this 9.8, this is sometimes called gravitational acceleration. Okay, so this is basically the Earth, gravity at the surface of the Earth. This is how fast objects accelerate if there's no air resistance. So it's a pretty good approximation for dropping a ball off a building. Okay, so what we see is that even the function is given in terms of t squared, but the acceleration is constant. So the acceleration is 9.8 meters per second squared, no matter where the ball is in the motion, at least until it hits the ground, right? Until it hits the ground. Okay, so the acceleration doesn't change. The velocity changes. The velocity gets faster the more time elapses. You drop the ball at first, it starts out not moving at all. As it falls further, it starts moving faster. But the acceleration is due to gravity, and that's just a constant based on the shape and the density of the Earth. Okay. So, I mean, of course, it's not actually constant because the ball's a little bit higher at the top and it's a little bit closer to the Earth's core at the bottom. But for all practical purposes, these differences are not really observable. So the gravitational constant is basically a constant near the surface of the Earth. Sometimes people just round to 10 just because maybe you don't have enough precision to measure to 2 decimal places. 9.8 is more accurate, but if you only need 1 decimal place of accuracy, it's okay to use 10 and it's easier to compute with it. But 9.8 is more accurate at the surface of the Earth. But maybe your watch only has, 1 decimal place of accuracy, in which case the 9.8 is an insignificant figure, so you don't need to use it. You can just use 10 instead. Okay. All right, any other questions on this? Which dimension does it support? I don't understand the question. Oh, dimensions? Well, this is I mean, the units are meters per second squared. Here. Sometimes it's written as negative 9.8 meters per second squared because we're orienting it as f of t is the height. But in this case, I
Yeah.
said it's the meters below the top, so
Hello.
it actually becomes positive. Yes, enough.
Yeah. What if you have the function? You have h of x equal f of x, all divided by g of x. Or what can a person say about the derivative of that function? Will it be the same f prime of x over g prime of x?
No. So there's a
And
quotient. Yeah, you can't.
yeah, so now it's not matter that you will use the quotient rule, right?
Right. So we're going to talk about that next time.
Oh, okay, good.
Yeah. Okay, we're going to do that next time. So today is kind of about meaning and applications of derivative, and then next time we're going to do more formulas. Yeah, so in general, it's not just f prime over g prime. You have to do something more complicated called the quotient rule, which we'll do next time.
Yeah, hello.
Yes, hello?
Yeah, what if, for example, on a text, you give me a function to find its derivative? What if I use the L'Hospital rule, the L'Hospital rule to find it? Will that still be correct? Will it still be accepted?
Well, you can try to use the L'Hospital rule to find the derivative, but the problem with that is that you need to use derivatives to do L'Hopital's rule, right? So it's going to be hard to use it if you don't already know the derivative, because you have to use derivatives in order to find it,
Okay.
right? Yeah, you're gonna have to use derivatives to find. And L'Hopital's rule involved plugging in a derivative, so you need to know how to take the derivative in the first place. Oh, so I see. So this is one-dimensional motion. There is a version of this for two-dimensional. So you can talk about motions in 2 and 3 dimensions. Those are what are called vector-valued functions or parametric equations. And if you do that, this concept of velocity and acceleration still work. Velocity is still the first derivative, acceleration is still the second derivative. For now, we're only doing one-dimensional motion, but if you want to do motion in any number of dimensions, you can write it in the form like x equals f of t, y equals g of t. If you have two-dimensional motion, that's called a parametric equation. And then you can take the derivatives, that gives you velocity, and you can take the second derivatives, that's going to give you, oh, thank you for the spelling mistake. And that's going to give you the acceleration. Um, if if you do two derivatives. So it works in all dimensions, but for now we're just doing it in one dimension. So Princeton says, does the function need to be negative to find the derivative in this problem? We don't need negative because I told you what f of t means. It's measured in meters below the top of the building. So here we really have, this is, um, let me write this. So here, if we're looking at our position axis, if s equals f of t, this here is s equals 0, and then s equals 1, and then s equals 2, and so on. So I'm orienting my axis so that the numbers get bigger as it falls. But often in a physics problem, you will see minus 4.9t squared instead of plus 4.9t squared. And that's because you're orienting things with a certain amount of height above the ground. So moving up is positive position and moving down is negative position. The way I set up the problem, I have moving down is positive for position, and that means that we only need to use a positive constant. But you could change your axis to have this could be -1 and this could be -2, in which case you would have a minus here. Okay, it all just depends on how you set up and define your variables. Okay.
Yes, Dr.
Yes,
Obus.
Princeton?
Yes, with the question just posted, looking at this position
Mm-hmm.
of this person at the top of the building and
Mm-hmm.
trying to drop this ball on the floor, right?
Yeah.
Why in case the person is standing on the floor?
Oh, okay. So if the person is standing on the floor, okay. So if you're standing on the floor and you just drop the ball, then nothing happens. If you're standing on the floor and you throw the ball up, then you have a different
Yeah.
equation of motion. Okay, I want to see, are we doing that? This is a homework example. Okay, ball is thrown vertically upward with an initial velocity of 80 feet per second. So maybe let's hold off from that. It's going to be one of the homework questions. We'll discuss it then. Okay. So that's going to be a homework question. What happens if you throw the ball up? What turns out is that the acceleration is the same no matter what you do when you start. The gravitational acceleration is just what acts on all objects near the Earth's surface. So it's always 9.8 meters per second squared toward the ground. And it doesn't matter what your initial velocity is or what you do. The gravitational acceleration is always the same. Yeah. Okay, any other questions about this example? Okay, great. Okay, let's move on. Okay, so let's just do another example. Let's say that we have a particle moving horizontally just on an axis. It's just an axis. This is 0 here. And it's given by f of t equals t cubed minus 6t squared plus 9t. where t is measured in seconds and f of t is in meters. So we have a question. So this is a few questions. So when is the particle at rest? When is it moving forwards? When is it moving backwards? And what is its acceleration function? Let me actually draw the diagram a little bit further down. Okay. So the first thing, so to answer any of these questions, we're going to need to take derivatives, right? So we're going to have, f of t we've seen is t cubed minus 6t squared plus 9t. F prime of t, we know how to take what we're going to have to take two derivatives to answer questions about velocity and acceleration. So f prime of t is 3t squared minus 6 times 2t plus 9 times 1, or 3t squared minus 12t plus 9. And then f double prime of t is going to be 3 times 2t minus 12, right? Because the t squared becomes 2t, and the 12t just becomes 12. The 9 just goes down to 0. And so this becomes 6t minus 12. Okay? So these questions, which I'm going to step away for, I have to step away for a couple of minutes, but you can think about these questions. So maybe this first question, when is the particle at rest? And when is it moving forwards and when is it moving backwards? I guess we've already answered one of the questions. This is the acceleration function.
Yeah.
Right. Yeah.
Hello.
Mhm. Yes.
Yeah. So, can I make a term on the first question?
Let's wait 2 minutes. Let's give everybody a little bit of a chance to think about it for 2 minutes, and then we can do a demo.
Okay.
All right. I'll
Okay,
be right
sir.
back in 2 minutes. Okay. Hmm. Okay. Okay. So I see Princeton has a great comment. The particle is at rest when its velocity is 0. That's exactly right. Right? So particle is at rest when velocity equals 0, right? I wasn't speaking. I was stepped away for 2 minutes. So particle is at rest when velocity is 0, so we can set,
Yes.
yeah, Princeton, yep. You want to,
So
yep. Mm-hmm.
looking at the moving forward,
Mm-hmm.
when it's moving forward, you will see that the time will be equal to 1, and
Mm-hmm.
then that of 2, that of 3.
Right. Mm-hmm.
Yeah. In that case, you have where we first they have 3t squared minus 6 minus 12t plus 9.
Mm-hmm.
So what I have to do now is to just divide both sides by 3,
Okay. Right.
which
So
will
this is
get t
3
squared
times.
minus 4t plus 3. And then you just have to just use of factor or no. You use your
Okay.
simplify, I think so. Yeah.
Mm-hmm.
So you get t,
Yep.
so t minus 1 and t
Mm-hmm. T
plus 3.
minus 3, right. Great, exactly.
So t now will be equal to 1 and t equal to 3.
Perfect. So this is when the particle's at rest, right? T equals 1 and t equals 3, right? So we need to check. So that's exactly when it's at rest, at t equals 1 and t equals 3, because we check to see when the velocity is 0, right? Now, we also want to know when is it moving forwards and when is it moving backwards. So let's look over here. If this is 1 and this is 3, we know that at t equals 1, it's at rest. At t equals 3, it's at rest. It can be changing directions during this time. So we have to look and see when is this velocity function positive and when is the velocity function negative, right? So when t is bigger than 3, right, both of these terms are positive. T minus 3 and t minus 1 are both positive, right? So if we're looking at f prime of t, our velocity function, when t is bigger than, if this is the t line, then when t is bigger than 3, it's positive. When t is between 1 and 3, the t minus 1 is positive, but the t minus 3 is negative, right? So it's going to be negative here. And when t is less than 1, the t minus 1 is negative, and the t minus 3 is also negative, which means they're both, their product is positive. So what we see is, let's imagine we start at time 0, that from time 0 to time 1, the particle is moving forward. Then from time 1 to time 3, the particle is moving backwards. And then from time 3 onward, the particle is moving forward again. Right? So this corresponds to, forwards for these two parts, and then backwards, sorry for the writing so small, backwards, this part in the middle. Okay? Right? And then at rest is exactly at 1 and 3. That's when it's at rest. And at rest is what happens when the particle goes one way and then it has to stop and change directions the other way. The particle's at rest during that little part. So what we have to do if we want to draw a diagram to represent the motion, maybe on this line, if this is our position axis, maybe we'll call it S, then what we need to do is we have to start at t equals 0. It moves forward to t equals 1, then backwards to t equals 3, and then forward again. So we need to know what these points actually are. So what's the position? Well, at t equals 0, we can just plug in. We see that f of 0 is equal to 0. So the particle is going to start here at 0. F of 1, which is when it starts moving backwards. So f of 1 is 1 minus 6 plus 9. So f of 1 is going to be equal to 4. And then f of 3, if you calculate it, you have 27 minus 54 plus 27. So this actually turns out to be 0 again. So what actually happens is what the particle does is it moves from 0 up to 4, then it turns around and goes back to 0. Oh, no, I don't want this. Sorry. Then it turns around and goes back to 0. and then it turns around again and keeps moving forward for the rest of time. Okay? So this is maybe a diagram of what's going on with the position. In terms of time, this is going from t equals 0 to t equals 1. I'll call this here f of 1. And then going backwards to f of 3, and then moving forwards for the rest of the time. Okay, and we can see that the velocity function is telling us when it's moving forwards and backwards, and it also tells us these times at time 1 and time 3, that's when the particle's at rest. That's exactly when the particle turns and starts changing directions. That makes the particle be at rest. Okay. And if you want to, this isn't part of the question, but the acceleration function, this 6t minus 12, what we see is that the acceleration is positive up until, hold on, I'm getting confused. Oh, right. The acceleration is negative up until t equals 2, when it becomes 0, and then it becomes positive. So what we see is the particle's moving to the right, but it's slowing down, slowing down, slowing down until the point where it turns around and now starts moving to the left faster and faster, faster. But then here, at some point here at time 2, the acceleration stops. And so instead of moving faster, it starts moving slower and slower and slower, and then it finally slows down, and then it starts moving faster and faster and faster to the right. That's what's going on with this acceleration. The acceleration is negative when t is less than 2, so it's kind of facing a headwind. It's being pushed to the left. And then once t is greater than 2, it's positive. So you can imagine a force on the particle pushing it to the right after t equals 2. Okay. Any questions on this example? Okay. All right. So I want to talk a little bit about derivatives graphically. So we've talked about them algebraically a lot today. So I want to talk about them graphically. So let's remember that the derivative of f of x represents the slope of the tangent line to the graph of y equals f of x. And so we can sometimes use this to draw the derivative of a function using only graphical input, even without a formula. Okay? So what's an example of this? So, okay, I wanted to find a particular example. Where's the example that I want? Yeah, here we are. Okay, so let's say here's my graph y equals f of x. So I'm going to have a graph that looks like this. Okay, this is my graph. This is some function y equals f of x. I'm not going to give you a formula for it. Okay? And what we want to do is we want to draw, maybe on the same set of axes, let's try to draw, in red, we want to draw y equals f prime of x. And so the point is, let me maybe we'll start f of x here. Maybe it starts at x equals 0. Okay? So we have to understand what's going on with the tangent lines here. And one of the things that's useful is to kind of draw the spots where the tangent line looks like it's horizontal, right? Tangent line over here looks like it's horizontal, over here is horizontal, and then over here maybe the tangent line has a negative slope, and then it has positive slope going up to here. The slope maybe gets the highest here and then flattens out again, and now the tangent line has negative slopes, maybe all the way down to here. The tangent line has negative slopes. Okay? So what we're trying to do is we want to sketch the graph of the derivative. That's the function that at any given point, its value is the slope of the tangent line of the original function. Okay? And so we can do this without any formulas, just by looking at the graph. maybe before we do it, I should notice, look at these places where the tangent line is flat. This looks like it's flat at the maximum value here, right? That's not an accident. And this is maybe not the minimum value of the function, but it's the minimum value. It's what's called a local minimum around the neighborhood. So we'll talk about that a little bit longer, but one of the major applications of calculus is that you can use these horizontal tangent lines to find the maximum and minimum values of functions. Okay, this is one of the most major applications, probably the most important application of calculus, is to find maxima and minima of functions. Okay, so we're going to do that on December 20th. We'll talk a little bit more about that. But for now, it's just an interesting observation. Note that when the function takes its maximum, you see that it's got a horizontal tangent line there, okay, which means the slope is 0. It's going to be good for algebraic computation. Okay, so back to our problem. Let's try to graph y equals f prime of x. I'm going to graph it in red. And well, the first thing to notice is, well, here the slope of the tangent line is 0, and here the slope of the tangent line is 0. So whatever the graph of my derivative is, it better be 0 at these x's, right? And so what's happening over here? Well, before I get to this line, it looks like the slope of the tangent line at all of these places is negative. It's kind of going downward, but it's only very slightly negative, which means that the derivative as a number is just going to be some very slight negative number. So this section of the derivative, it has to go from being very slightly negative to 0. So maybe this section of the derivative probably looks something like this. Okay. It goes from, let me try to draw that a little more curved. So it goes from a slightly negative number to 0. Now what happens here? Well, to go from here to here, well, here the derivative is 0, here the derivative is 0, but everywhere in the interim here, I'll draw a couple more tangent lines or tangent line segments, right? These slopes here are positive of these tangent lines, right? These are all tangent lines with positive slope. So it seems like it gets to a biggest slope somewhere here in the middle, and then the slope goes back down, winding up at 0 over here. So the way this might look is it goes up to a slope here in the middle, and then it goes back down to 0. Maybe the most rapid rate of change, or the steepest tangent line, is somewhere, I think it's a little more accurate. It probably gets to its peak a little bit before the middle, something like that. Maybe even a little bit before that. Yeah, so it kind of hits its peak over here, which is the highest slope that the tangent line takes, and then as it gets down to here, the slope goes down back to 0. Now what happens? Now the slope of the tangent line becomes negative, right? I'm going to draw a few representative tangent lines, right? This is negative here. Over here, it's even more negative, and so on. And then it starts to flatten out a little bit as I go toward the end, right? So the slope starts getting a little negative. It gets very negative here. This is a very steep descent. And then the descent starts to flatten out. And over here, as we go on, it kind of almost looks like a straight line. So the way that looks like graphically is that it's going to go down to some very negative value. Maybe over here, this is this very steep negative slope. And then it's going to level up. It's still going to be negative, but it's not going to be as steep. And at the end, this almost looks like a line. This almost looks like this tangent line is going to start to have pretty constant slope as the graph goes on. So this is going to go back up, and then maybe it's just going to start looking pretty flat as the graph goes on. Okay, so this is not an exact science to draw the graph, but you want to be able to hit the main features of the graph of the tangent line. So this over here should be y equals f prime of x. Okay. The idea is you want to know, when is it negative, when is it positive? That corresponds to when the function has negative slope of the tangent line, when it's decreasing, or when it's increasing, positive slope of the tangent line. You want to know when it's going to go past 0. Those are going to be the horizontal tangents. And you want to know kind of when it starts, when is the tangent line, very, very steep, and when is it a little less steep? That's what's going on here. It's getting less steep over here. And this allows you to sketch the derivative of the function, even though we don't have a formula. We're not evaluating any limits. We're just using it based on the graphical information that comes from the slope of the tangent line. Okay. We could do this with second derivatives also, although I think I'm going to wait up. I don't want to do that today. There's kind of a lot of new concepts today. I'm going to keep only the first derivative today. Okay. All right, so this is a way of sketching the graph of f prime of x. I want to do one more example of this, but first
Yeah,
questions.
hello.
Yes, enough.
Darabal?
Yeah.
Yeah, I beg you. I want you to explain this in detail because it's so interesting. I want you to explain how you can find f prime of s of the function from its original function on the graph.
Yes. So we're going to do that's the next example.
And after that, we take another example.
Yeah. Okay. Yeah. So this is exactly going to be the next example. Okay. So we're going to do this algebraically next time. But for this time, let's look at the graph of y equals sine of x. So we know what this graph looks like. It looks like a sine wave. So this goes from -1 to 1, and the graph of sine of x looks like this. I'm going to draw one section, maybe two sections of the graph of sine of x. Okay, so let's say this is what it looks like. Maybe I'll only draw this part. So if you remember from trigonometry, this here is pi, this is 2 pi, this is negative pi, and this is negative 2 pi. This is the graph of y equals sine of x. Okay.
Yeah, sure. That's it. Yeah, that's it.
So we'll draw it between -2 pi and 2 pi. It just repeats after that. So it's good enough to draw it here. So now graphically, let us draw y prime, right? Remember, y prime was another notation for the derivative, right?
Yeah,
so we're going to do.
Okay. I understand now. So now y prime, you now have cosine x. Okay, I understand.
Okay, but we don't know. Okay, I mean, you know that it's cosine x, but we haven't shown that it's cosine x yet.
I understand. And now there is just a slight difference between the graph of sine x and that of cosine x. I understand how the graph goes.
Right. So let's do it. I mean, so it turns out the derivative of sine x is cosine x. This is kind of giving away the game. We'll prove this algebraically next time. But what I want to do today is let's just draw. Let's just use our visuals to draw this and see why it looks like cosine x. So what is y prime? Remember, it's the slope of the tangent line. So if we start over here, the slope of this tangent line looks like it's about 1, right? This looks like the line y equals x. So if we're drawing our graph of y, it looks like it should start at 1. Now let me draw all of the horizontal tangent lines here, right? Every time when we hit the top or the bottom of the wave, we get a horizontal tangent line. So at all of those points, the slope of the tangent line is 0, right? So whatever this graph of the derivative is, it should pass through 0 wherever there are these horizontal tangent lines. And so what happens? Well, the slope of the tangent line here is 1, and it starts getting less steep, less steep, less steep until it gets to the top here, where it turns out that the slope becomes 0. And so this steepness actually decreases pretty rapidly. So what's actually going on with the slope of the tangent line is it's going from 1 down to 0. So the slope of the tangent line in this segment is going to look like this. Okay, right? This is y prime is equal to, y prime, or, it's y equals whatever the derivative of sine of x is, right? So now what happens? Over here, the slope looks like it's going to be -1, right? Because this looks like it's kind of y equals negative x going through pi, right? It looks like it's got a slope of -1. So this is going to go all the way down to -1 over here. And what happens, it starts from a slope of 0 and then goes up to a slope of -1. Sorry, it goes down to a slope of -1. So this is going to look kind of like this. Now we have the same thing here. We start with the slope of -1. Tangent line's getting shallower and shallower, and eventually over here, they're rising back up to 0. So this goes from -1 back up to 0 like this. And then lastly, here we have a slope of 0, and by the time it gets back to 2 pi, well, we know that at 2 pi, it's the same as at 0, right? Because sine, when you add 2 pi, it doesn't change anything. So that means if the slope here was 1, then the slope here is also going to be 1. And what that means is that the slope is going to rise from 0 down here up to 1 over here, and it's going to look like this. Okay. And now we can do the same thing the other way. Right here, the slope is 1, and down here, the slope is 0. It rises from 0. The slope rises from 0 up to 1. So it's going to look like this, 0 up to 1. And then over here, we have the slope is 0 here, and then over here at pi, maybe I didn't draw it so well over here, but this slope should actually be -1 over here. It looks a little steeper than -1, but it turns out it's actually -1. This is just because my drawing on the left side is not as good as my drawing on the right side. So this should be -1, which means the derivative is going to go down from 0 down to -1. And then between pi and here, we have a slope of -1. Here's a slope of 0. It's getting steeper and steeper until it's actually -1. So that means the slope is going from 0 down to -1. And then lastly, here we have a slope of 1 of the tangent line. It's getting shallower and shallower until it goes down to 0. So we have 1 going down to 0 here. Okay, so this red is whatever it is. This red is just y equals d dx of sine of x. And so this leads you to ask the question, well, this looks like sine. This derivative graph looks kind of like the same curve, just shifted over a little bit. And in fact, it looks exactly like the cosine curve, right? The cosine curve is the same as the sine curve. It's just shifted over. It starts at 1 instead of starting at 0. So this is a very reasonable question you can ask. Is the derivative of sine of x equal to cosine of x? Okay, it seems very reasonable by looking at this graph for that to be the case. And the answer, in fact, is yes. Okay, and we'll show this next time. Okay, so we're going to show this next time, right? That the derivative of sine is cosine. And we're going to show this using algebra and using limits and even using a little bit of geometry and trigonometry because we have to evaluate certain limits. But the point is, even before we do any of this, we could get, if we know what the graph of sine looks like, we can draw what the graph of its derivative has to look like. It's got to look something like this. And then we recognize this. We're like, oh, this looks like cosine. So maybe the derivative of sine is cosine, which is really kind of surprising and beautiful. And it turns out that that is true, that the derivative of sine is cosine. And so we're going to talk about that, how that works next time. But we already have some reason to believe this from just understanding what the slope of a tangent line means and how graphically we can draw it. Okay, so this is kind of setting us up for what we want to do next time when we're going to talk about derivatives of trig functions and product rules and quotient rules. We're going to do a lot of formulas for derivatives, but I wanted to spend a little bit more time today talking about what derivatives mean in terms of velocities and slopes of the tangent line and what it means to be differentiable. So that's kind of the focus for today. Next time, the focus is going to be a little bit more on algebra and formulas. And then on December 20th, the last day for the fall, the focus is going to be on applications to optimization, maximizing and minimizing things. Okay. So that's what we have for the example now. Questions on this example, by the way?
Great. It's good.
Yep. You know?
Yeah, I said it's okay. It's okay. I understood.
Okay, great.
Yeah.
Okay. So here's some homework exercises. So first, very straightforward exercise. Find the first, second, and third derivatives of 2x squared minus 5x plus 8. This is just some practice with derivatives. This shouldn't be very difficult. Second one, a ball is thrown vertically upward with an initial velocity of 80 feet per second. Then its height after t seconds is given by this equation. F of t, oh, this should be an 80. Sorry, I wrote this wrong. 80t plus 80t minus 16t squared. Here, height f of t is in feet, not in meters. Okay. So the question is, what is the maximum height that the ball reaches? And hint, just like what we did, what is its velocity when it reaches the maximum height? What does the path look like? And once you know what its velocity is when it reaches the maximum height, then you can figure out what time it reaches the maximum height, and you can figure out what the position is from that time. So that's question number 2. And question 3 says when a dead rechargeable battery is plugged into a charger, here's a function C of t, which represents the percentage of charge recovered after being plugged in for t hours. So I'm going to draw you a graph of y equals C of t. I'm going to draw it right here. Okay, so this is t. This is my axis, which is measured in percent. So it's 100%, 50%, 0%. So we start with a dead battery. It's at 0% at time t. And this is how the graph of the charge looks like. So you plug it in, it starts getting charged very rapidly. And as it gets toward 100%, it kind of levels off. Okay, so this is the graph y equals C of t. And what I want you to do is do something similar to what we did in these last 2 examples. Can you draw a graph of the derivative of c prime of t? I'm not giving you a formula. I'm just drawing you this graph. So the question is, can you draw a graph of what the derivative has to look like? And then another question, challenge question, is what is the meaning of c prime of t? What does this mean in terms of electricity, in terms of the battery? Okay, so can you give an interpretation of what this c prime of t means? Okay, so these are the homework exercises for this week.
Yes.
Yes, Princeton? Yep.
Yeah, where you have F of T, is that it you put there?
That's an 8. Yeah, sorry. It
That
said
it? I don't know.
20. I made it 80. Yes, 80. Sorry, that's 80. Let me just say
Okay.
80t minus 16t. Let me.
Okay.
Oh, sorry. Yeah, this is fine. 80t minus 16t squared. Let me erase this. 80t minus 16t squared. No, originally it was going to be 20 meters, and then I changed it to 80 feet, but I forgot to change the function. Okay, so what is the meaning? So these are the homework questions. Thank you, as always, for your attention. So next week, December 13th, we will have class, and we're going to discuss further rules for differentiation, the product and the quotient rule that we talked a little bit about today, but we're going to actually do them. And then we'll also discuss differentiation of trigonometric functions. So we'll actually show that derivative of sine is cosine, and we'll show that you can do a lot of the other trigonometric functions also by combining that with the product and quotient rule. Okay. So again, if you forgot to put your name in, please put it in now. But I think everybody has put their name in at some point. So, but if you forgot, now is your chance before I stop the recording to put the name in. I think everybody remembered though. Okay. Okay, so I hope everybody has a great week and a great weekend, and I will talk to you next week. And as always, I'll send out the questions, I'll send out the notes, and I'll post the video to YouTube. Okay, let me stop the recording.